Hello friends, this is the second part of my presentation, solid state. So in the first part of this presentation, I discussed regarding solid, that is crystalline solid and amorphous solid. Crystalline solid are the pure solid, amorphous solid are not pure solid. And in that video also we discussed spatialities, what is a spatialities. Then we discussed what is unit cell. We discussed what are primitive and non-primitive unit cell. So today basically we'll be discussing about the number of units per unit cell. Then we'll be discussing the packing fraction or packing efficiency of an unit cell. Then we'll be discussing the density of cubic unit cell. So just I will turn to where we left in the other class, that is where we left about unit cell, different types of unit cell. Now we will be starting our new class. So these were the three types of unit cell we discussed last class. This is simple cubic unit cell where units are present only at the corners. There are no unit cell, there is no unit present at other places. So it is called a simple cubic unit cell, and this is an example of a primitive unit cell. This is a BCC unit cell where units are at the corners as well as one unit at the center of the cubic unit cell. And this is an FCC unit cell where units are at the 8 corners and each face has one unit at its center. So these are the three different types of unit cell in the cubic system. This is a simple cubic unit cell, this is a body-centered cubic unit cell, this is the face-centered cubic unit cell. Now this unit, it is present at the corner, and from this picture it is clear that this unit is shared by 8 unit cells. 1, 2, 3, 4, 5, 6, 7 and 8. So this unit is shared by 8 unit cell. So the fraction of unit per unit cell will be 1 by 8. Similarly, this unit is at the center of a face. This is a face which is common to these 2 unit cells. So this unit is shared by 2 unit cell. So per unit cell, the fraction will be half for this unit. So half will be in this unit cell and half will be in this unit cell. So here, if a unit is at the center, then it belongs to only that unit cell. So its fraction to that unit cell will be 1. If units are at the corner, then each corner is shared by 8 unit cell. So the fraction of unit cell per unit cell will be equal to 1 by 8. Whereas if an unit is present at the face center and each face is shared by 2 unit cell, so the fraction per unit cell will be half for each unit present in the center of a face. Then what about an edge? So this is an edge of unit cell. This is an edge of unit cell, and this unit cell, the edge is shared by 1, 2, 3, 4 unit cell. So any unit at this edge will be shared by 4 unit cell, 1, 2, 3, 4. So per unit cell, the fraction of unit cell will be 1 by 4. So if an unit is at the center, its fraction in unit cell is 1. If it is in the face center, it will be half. If it is at edge, because each edge is shared by 4 unit cell, then the fraction of the unit per unit cell will be 1 by 4. And if the unit is at the corner, then per unit cell, its fraction will be 1 by 8. So this is a space lattice where the unit cell is a simple cubic unit cell. This is a cubic unit cell. So here then space lattice, you can see the unit cell is a simple cubic unit cell. All the units are at the corners. So each unit at the corner will contribute 1/8 towards unit cell. So there are 8 units at 8 corner. So the total contribution per unit cell will be 1/8 into 8. That one will be equal to 1. Then for FCC unit cell, the total number of units per unit cell is 4. Because each unit at the corner contributes 1/8, so 8 units, the total contribution will be 8 into 1/8 is equal to 1. And each unit at the center is contributing half towards the unit cell. So 6 unit will contribute half into 6, it will be equal to 3. So 3 plus 1, it will be equal to 4. Then in case of body centered cubic unit cell, the contribution by the units at the corners will be 1, and the unit which is at the center is not shared with any other unit cell, so it contributes 1. So total number of unit per unit cell will be equal to 1 plus 1 is equal to 2. So here, that is the summary. This is the simple cubic unit cell. Units are at the corner, and the total number of unit per unit cell is equal to 8 into 1/8. 8 stands for the number of units at the corner, and 1/8 is the fraction of the unit per unit cell, and it will be equal to 1. So a body centered cubic unit cell, the units at the corner will contribute 1/8. So 8 units will contribute 8 into 1/8, and the unit at the center will contribute 1. So the total will be 8 into 1/8 plus 1, it will be equal to 2. And with similar argument, for an FCC unit cell, the total number of units per unit cell will be equal to 4. How it is 4? 8 into 1/8 plus 6. 6 means there are 6 faces. So there will be 6 units at 6 faces. 1, 2, 3, 4, 5, 6. And each unit contributes 1/2. So it is equal to 4. Now we will try to find out a relationship between the radius of an unit and the edge length of the unit cell. So all these unit cells are cubic. So in case of a cube, the edges have same length. Let us say the edge length is A. So length, breadth, height, it will be A. Now in case of a simple cubic unit cell, this is a simple cubic unit cell where units are at the 8 corners, 1, 2, 3, 4, 5, 6, 7, 8. And now from this picture you can see the units are touching each other along the edge. This is one unit at the corner, this is another unit at the corner, and both these units are touching each other along the edge. Then again, this is one unit at the corner, this is another unit at the corner, and these two units are also touching each other along the edge. So the calculation is simple. So the edge length is A and the radius of an unit is R. So from here to here it is R, from here to here it is also R. So the total distance from this corner to this corner, it will be equal to 2R. That means A is equal to 2R. This is for simple cubic unit cell. Now what about for a FCC unit cell? We will talk about BCC unit cell later. So this is an FCC unit cell. You can see the units are at the corner 1, 2, 3, 4, 5, 6, 7, and one unit is somewhere behind this unit. And there are 6 units at the 6 faces. So this unit is the center of one face, this unit is center of another face, this unit is at the center of another face shown. So from this picture it is clear that unlike in simple cubic unit cell where unit touched each other along the edge, here in FCC unit cell the units are not touching each other along the edge. The units are touching each other along the face diagonal. So this unit at the corner and this unit at the corner, they are not touching each other. This unit at the corner and this unit at the corner, they are not touching each other. But this unit is touching this unit which is at the center of a face, and this unit is touching this unit which is at the corner of the edge, corner of the unit cell. So in FCC unit cell, the units touch one another along the face diagonal. Now you can easily calculate the relationship between A, that is the edge length, and the R, that is the radius of the unit. Now you see, we can draw a right angle triangle somewhere here. So the units are touching each other along the face diagonal, and suppose the length of this face diagonal is B. The length of this edge is A, and length of this edge is also A. So we get a right angle triangle here. And by Pythagoras theorem, the square of the hypotenuse is the square of the other two sides. So B represent the hypotenuse, A represent the length of an edge. So by Pythagoras theorem, B square, that is hypotenuse square, is equal to the square of the other two sides of a right angle triangle. Now what will be the length of B? So here you can see the B is the face diagonal, and this is R, that is the radius of one unit. This is the diameter of the unit, and the diameter of the unit will be 2R. Then again this is the radius of an unit. So the distance of the face diagonal, the length of the face diagonal will be R plus 2R plus R. It will be 4R. So B will be equal to 4R. So if you substitute 4R for B, then it will be 4R whole square is equal to A square plus A square. It will be equal to 16R square is equal to 2A square. So A will be equal to root over 8R. So in case of simple cubic unit cell, A is equal to 2R, and in case of FCC unit cell, A is equal to root 8R. Now what about BCC unit cell? This is a BCC unit cell. Units are at the corner. Units are at the 8 corner with one unit at the center of the cubic unit cell. So here again we'll apply Pythagoras theorem. So again from Pythagoras theorem, this edge length is A. And suppose this is the face diagonal, it is B. Face diagonal is B. And we already know that B is equal to 4R. Then what will be C? C is the face diagonal. So C square will be equal to A square. This is A, that is the edge length, plus B square. B square is the face diagonal, and B square means it is 4R. So if you substitute them, what you will get? You will get C square is equal to A square plus B square. B is equal to this is B. Already you have seen B is equal to 2A square from this triangle. So C square will be equal to A square plus B square is equal to 3A square, and A will be equal to 4 by root 3R. So we can, using geometry, we can easily find out a relationship between edge length and radius of an unit of cubic unit cell. For simple cubic unit cell, A is equal to 2R. For BCC unit cell, A is equal to 4 by root 3R. And for FCC unit cell, A is equal to root 8R. So the summary, we got some summary that for simple cubic unit cell, the number of unit per unit cell is 1, and A is equal to 2R. For BCC unit cell, number of unit per unit cell is 2, and A is equal to 4 by root 3R. And for FCC unit cell, number of unit per unit cell is 4, and the A is equal to root 8 R. Now we will be calculating another important thing that is called the atomic packing factor or the packing efficiency. Now what is atomic packing factor or packing efficiency? Now, since we are considering that the units are spherical, so in a simple cubic unit cell, the entire volume of the unit cell will not be occupied by atom. So here from this picture you can see these are the 4 units at the 4 corners, and there is an open space in between them. These are the 4 units at the 4 corners, so there is an open space between them. So this space is unoccupied and we call them as voids. So here also you can see this void here. These are the void, these are the void, these are the voids. So as we assume that the units are spherical in shape, so all volume of the cubic unit cell is not occupied. So packing factor or packing efficiency is a measure of the amount of volume which is occupied by the units. And how do we calculate atomic packing factor? Atomic packing factor is the ratio between the volume of the atoms in unit cell, that is the total volume occupied by the units in the unit cell, to the volume of the unit cell. So definitely the total volume occupied by the atoms in unit cell is less than the volume of the unit cell. So the packing factor will be definitely less than 1. Now since we have regarded that the particles or the units in a crystalline compound are spherical, that is the atoms are spherical, so the volume of an atom is given by 4/3 pi r cube, where r represents the radius of the sphere, that is the unit, and the edge length of the cubic unit cell is a, so the total volume of the unit cell will be a cube. Now let us try to find out the packing efficiency for simple cubic unit cell. So this is a simple cubic unit cell. So these are the units which are at the corner, and these are the voids, these are the open spaces, these are the volumes which are not occupied. The edge length is a, and we already know for simple cubic unit cell a is equal to 2r, where r represents the radius of this unit, and the number of unit per unit cell or the number of atom per cubic unit cell is equal to 1. So the total number of atoms present in a simple cubic unit cell is 1. So the total volume of the atoms occupying a simple cubic unit cell will be 4/3 pi r cube. Now the volume of the unit cell is a cube, and the relationship between r and a is equal to 2r for simple cubic unit cell. So we substitute the values, we find the atomic packing factor is equal to total volume occupied by the atom, which is 4/3 pi r cube, to the total volume of the cubic unit cell, that is equal to a. Now substituting 2r for a, we get 4/3 pi r cube, that is the volume of an atom, by 2r cube, and it will turn to be 0.52, and in terms of percentage it is 52%. Now what does it mean? It means that in simple cubic unit cell only 52% volume is occupied, rest 48% is void. Now what about an BCC unit cell? So this is a sketch of an BCC unit cell. These are the units at the corner, these are the units at the corner, and this is the unit at the center of the cubic unit cell. So here also you can see there are a lot of open spaces. So the entire volume of the unit cell is not occupied. There are empty spaces. Now in case of BCC unit cell, the number of atoms per unit cell is 2. We have already calculated. And the edge length is A, and the relationship between A and R is 4R is equal to root 3 A. That means A will be equal to 4 by root 3 R. A will be equal to 4 by root 3 R. So the atomic packing factor 2, because the number of units per BCC unit cell is 2. Total volume will be 2 into 4 by 3 pi R cube by 8 A cube, and A is equal to, your A is equal to 4 by root 3 R. So we substitute A as 4 by root 3 R. And this A must be R. Some mistake is in the slide. So this should not be A, this should be R. Then R will cancel each other. Then you will get 0.68. So in terms of percentage, it is 68%. So in simple cubic unit cell, 52% volume is occupied, and in BCC unit cell, 68% volume is occupied. Now what about FCC unit cell? In FCC unit cell, we have units at the corners and units at the center of faces. And the relationship between A and R is 4R is equal to root 2A. That means A will be equal to 4 by root 2R. So in case of FCC unit cell, the number of atoms in FCC, this should be FCC. There is some printing mistake in the slide. It is 4. Then volume of atom is 4 by 3 pi R cube. So the total volume occupied by the atoms will be 4 into 4 by 3 pi R cube. And the volume of the unit cell is A cube. So we substitute A by 4 by root 2 R. Then it will be 0.74. So in terms of percentage, it will be 74%. So our summary is that in case of simple cubic unit cell, the atomic packing factor or packing efficiency is 0.52. For BCC unit cell, it is 0.68. And for FCC unit cell, it is 0.74. Diamond, you know, it's a crystalline compound where each carbon atom is tetrahedrally bonded to 4 carbon atom. Here the packing efficiency is only 0.34. That means most space in diamond crystal is empty. Then these are the number of atoms per simple cubic unit cell. It is 1. For BCC it is 2. For FCC it is 4. For hexagonal close packing it is 6. And for diamond it is 8. And the relationship between radius of an unit and edge length, for simple cubic 2R is equal to A. For BCC it is 4R is equal to root 3A. And for FCC it is 4R is equal to root 2A. For ACP it is 2R is equal to A. And for diamond it is 8R is equal to root 3A. So here we have discussed 3 types of cubic unit cell. That is simple cubic unit cell, the FCC unit cell, the BCC unit cell. So in simple cubic unit cell, number of units per unit cell is 1. Then the total volume occupied is only 52%. That means most space in simple cubic unit cell is vacant. In BCC unit cell, the number of unit per unit cell is 2, and the volume occupied is 68%. that means 32% volume is void. And in FCC unit cell, the total number of unit per unit cell is 4, and the total volume occupied is 74%. So these are some parameters of cubic unit cell. That is simple cubic, body-centered cubic, and face-centered cubic. Now I can also calculate the density of a cubic unit cell. You know, calculation is simple. You know, density is mass by volume. So the density of a cubic unit cell will be the mass of the unit cell divided by volume of the unit cell. Now mass of the unit cell will be equal to the number of unit per unit cell. For simple cubic it is 1, for BCC it is 2, for FCC it is 3, it is 4, FCC it is 4, and the volume of unit cell is given by AQ. So the mass of the unit cell is Z. Z will be 1 for simple cubic, 2 for BCC, and 4 for FCC. And mass of one unit will be given by M, that is the atomic weight divided by Avogadro number. So this will be the mass of the unit cell. And what will be the volume of the unit cell? It will be equal to AQ. So substituting mass and volume by Zm, Na, and AQ, we find the density of a cubic unit cell is Zm, Na, AQ, where Z will represent the number of unit per unit cell, and it will depend upon the nature of the cubic unit cell. If it is simple cubic, Z will be 1, for BCC it is 2, for FCC it is 4. M, it will be atomic weight, Na represent the Avogadro number, and A represent the age length. So this is a problem. When silver crystallizes, it forms face-centered cubic cell. The unit cell length is 409 picometer. Calculate density. So density is mass by volume. So here volume is AQ. A is the age length. It is 409 picometer. 1 picometer is equal to 10 to the power of minus 10 centimeter. So 409 picometer cube will be equal to 6.83 into 10 to the power of minus 23 cubic centimeter. And in FCC unit cell, there are 4 atoms per unit cell, so Z will be equal to 4. So your mass of a cubic unit cell will be equal to 4, because it is an FCC unit cell. Mass of an silver atom, it will be equal to 107.9. It is the atomic weight of silver divided by Avogadro number. So the mass of an cubic unit cell, FCC unit cell, will be 7.17 into 10 to the power of minus 22 gram. So the density is the mass of the cubic unit cell divided by volume of the cubic unit cell. It will be equal to 10.5 gram per centimeter cube. So in today's class, we discussed the different types of simple cubic unit cell. More really, it is a cubic unit cell, and cubic unit cell may be simple cubic, where units are occupying only the corners, or it may be a body-centered cubic unit cell, where units are occupying the corners as well as body center, and the FCC unit cell, where units are present only at the corners as well as center of the faces. Then we discussed the number of unit per unit cell. We discussed the packing efficiency. We discussed the relationship between radius of an unit cell and the edge length of the unit cell. And finally, we discussed the density of an unit cell. So in the next class, I will be discussing cloche packing. What is the meaning of cloche packing? And we'll be discussing ionic crystals. So until then, goodbye. Have a good day.